Recording progress.
And I'd like to begin by doing a little recap where we are in this course. We discussed in the first chapter the introduction. We function. We considered how to calculate various state functions. Such as the energy, pressure, work and heat, and the entropy. And we then went on to factor out the partition function by consideration of the various degrees of freedom. In particular, the factoring out was done with these energetic modes, right? We considered that solutions to Schrödinger's equation can be written in terms of additive contributions that result from separate, or that result from approximately separate physics. So for translation, for example, we can write one Schrödinger equation, and for rotation, we can write another one. And they result in corresponding eigenvalues, and all these eigenvalues coming from these different physics, they can be approximately added up. And that enables us to factor out the partition function and to consider the StatMech contribution from each of these different physics modes separately. So in particular, we looked already at the translational partition function, at the rotational, and we started before reading week with the vibrational, tra, rot, and vib. We will then, just a little glance in the future, also discuss the electronic partition function. And then my plan is to move to the fifth chapter, which will be dealing with equilibrium constants. So this is sort of the backbone of this entire course. And with the tutorials, we try to accompany this and enable you to go also through the details. And of course, in terms of the final exam, we will draw from this entire table of content, right? Okay, now I lost my pen. Let's see, is it this one? Yeah. Okay, so let's then continue with the vibrational partition function. Which we had started before the reading week. Remember, we are considering, or we are doing this in the beginning just with the diatomic molecules, right? So if we go back at what we discussed, here we have this kind of system, two atoms, and of course, a covalent bond, a chemical bond, is not a spring. Right? However, for that particular motion, for that particular physics, this idea that the potential in which these two atoms move, right, for the vibrational physics, that this is a quadratic potential. Right? That's really not a bad idea. Right? So what this means was shown here in this figure. Right, we put this quadratic k r squared potential in our Hamiltonian, and as you consider the equilibrium regime, right, if your atoms are vibrating in the lower states, which turns out to be a rather good approximation, contrary to the rotational movements, right? Which was just a question I asked in the beginning of this course, of this lecture, today's lecture. That's really not a bad approximation. And the anharmonicities matter for the excitations then, right? In particular, as you start associating covalent bonds, right? Then, of course, assuming that your atoms are held together like springs is not a good idea. All right, we then, again, just like in the previous cases, took the solution which you already discussed in previous courses for vibrations. We took the solutions for the vibrational Schrödinger equation, and with the harmonic oscillator potential, right, with this parabolic potential, those are the solutions where nu has to do with the effective mass and with the force constant of the potential you're using for your spring. Okay. Now, we did a little trick to be able to get to the partition function more easily to a closed form solution by shifting the spectrum away from the 0-point vibrational energy. So your ground state already carries some movement, right? And this is an outcome of the Schrödinger equation. It's a quantum effect. If you consider classical physics, in the ground state, the atoms would not move. Right? So we shift this energy contribution away, right? And later on, we will be adding it back in, right? Once you do that, you can see that your partition function becomes, can take this the series form, geometric series, and there's a closed form solution for this, right? Which you see down here. So 1 over 1 minus e to the minus beta h nu is the vibrational contribution to the partition function. Now, you can quite easily see, if you use some plotting software, or if you can do it in your head, that this Q Vib with increasing temperature would start out low and become increasingly linear, right? So So this means that then once you think about that contribution to a state function like the energy or the entropy and so on, it just scales with temperature linearly. And that makes, again, an intuitive a development of the intuition how these state functions should change with temperature in terms of their vibrational contributions more easily available. Now, there's again, similarly to the rotational chapter, we do make use of a notation which is common also in the experimental branches in the vibrational spectroscopy, that we introduce a characteristic vibrational temperature for any given mode, okay? And this is the capital theta, the symbol we like to use for this, just like in the case of the rotation. And this is h nu over Boltzmann's constant. Okay, the mode n has a frequency mu, right? And so that's unless it's degenerate. When degenerate, it's the same. Then we have to count this twice. But so that serves as the indicator of which state we're talking about. Now, that is a definition, right? We define it as such. And then, of course, your Q vib simply becomes 1 over 1 minus e to the minus theta vib over t, right? So the Boltzmann constant in your beta was now swallowed by this characteristic temperature. And this has units of Kelvin, right? It's comes in units of Kelvin. So the exponent is unitless. So far, this is just notation and convention, and not so thrilling, but we can now insert back the 0-point shift. And we will not derive that in this course. We simply give you the solution, but one can show that Q vib becomes e to the minus theta vib over 2 times temperature over 1 minus e to the minus theta vib over t. So basically, you get this numerator due to the 0-point energy contribution. Now, again, this is the same as writing my default expression for my n vibrational states over these eigenvalues, right? And so this is extremely nice. It's a closed form expression. And this is exact, unlike the rotation and the translation, where we had to cheat a little bit and we also needed to shift quantum numbers. In this case, because we can fix it back again with the 0-point shift, this is exact. So it's an exact closed form expression. Now, these characteristic temperatures, of course, can be measured, right, from the frequency, the vibrational frequency. And you would find for a couple of diatomics, the following values. So for H2, your theta Vib in Kelvin would be 5,987. And if you then calculate the corresponding Q Vib at 300 Kelvin, you would get 1.000. Right? Now, remember that we multiply all these partition functions from the different modes of the energy, right? So the total partition function is then this product. And so if your partition function is 1, it basically means your vibration is irrelevant. Right? So in the thermodynamics of H2, at room temperature, vibrations are basically irrelevant, right? So that's what this means. Now, if I go to D2, what would you expect? Would the frequency, the vibrational frequency, go up or down? Right? If you have H2 and it vibrates versus D2, which one is vibrating faster? Anybody? Any guess? H2 is vibrating faster, absolutely. So the frequency is lower for D2, very good. And correspondingly, the characteristic frequency is only 4,307. Now, if you calculate your partition function, the vibrational part, for the last 3 digits, for the first 3 digits after the comma, there's no difference. Let's go to N2, one of the strongest bonds in this universe. And N2 is a triple bond, right? Should be quite stiff. So also high frequency. Now, please raise your hand if you believe the vibrational frequency of N2 is higher than H2. 1, 2. That's all I get. Now, I could, by the principle of by the principle of exclusion, I conclude that everybody else believes that H2 has a higher vibrational frequency. And in this case, the majority was right. Okay. indeed, H2 has a higher frequency, right? It's very important to realize, and again, the partition function will not change. So if you look at the bond energy as a function of the distance, the H2 bond will be above the N2 bond, but it will be much stiffer. So if this is N2, this is H2, okay? It's a weaker bond, but it's a stiffer bond. And so the frequency, which is related to the force constant, and the force constant, just so that you develop this intuition, this force constant here is the second order derivative of your potential, right? If you have a quadratic potential, you differentiate it twice, all you're left with is the force constant, right? So the force constant is the second order derivative, which is nothing else than the curvature. So if you have a stiff binding potential, the curvature is really high, the frequency will be very high. It does not mean that the well depth is large, right? It can be very high, it can be very a bond that's very weak, right? And it can still vibrate much faster. Now, let's go to Cl2. In this case, the frequency and now mass also starts to matter, has a strong impact. Now we have a vibrational characteristic temperature of just 800. And now you see for the first time an impact in your partition function. This means we now get something from the higher states, right? It's not just the ground state, there's something happening. And then if I go even lower to the bromine molecule, I have 463, and then I get 1.556. Okay. So you have to go to really heavy atoms with shallow bonds to see a modest impact on your partition function. Just for comparison, your Q rod at that temperature was on the order of 10, and the Q tra was on the order of 10 to the 30. Now, of course, when we discuss, for instance, differences between these different gases, you have a large translational contribution to each of the gas, right? And so if you consider the difference between them, which is typically what we do in chemistry, then the large translational contributions cancel. Any questions so far? Yes, please.
I don't understand where the term for the vibrational partition function for the numerator in the partition vibrational partition function came from.
You what?
Sorry, I don't understand where the term.
So we didn't show this. You just have to take my word for it now, right? But one can show that it looks like that, right? And it's exact also. So it's mostly in the interest of time. If you're really interested, you could also check with your tutor and see if you can discuss it in the tutorials. Any other questions? Okay, then let's go and look at the internal energy contribution. right? We have our cherished expression obtained in this course. Your nkbt squared, and now the temperature derivative of the logarithm of q vip, and this would be your vibrational energy contribution. Now, also here, doing this derivation takes longer, and so this is something which you should be seeing in the tutorials. The expression you should get looks like this. You get the characteristic temperature again over 2 plus theta vib over e to the theta vib over t minus 1. Okay. So this again, then for the molar energy results in your gas constant over 2 times vib plus gas constant d vib, and now divided by e d vib over t minus 1. So this is obviously vib not as simple as our 3/2 RT and 2/2 RT for tra and rot, respectively. So we do keep this, there is this vibrational internal degree of freedom, right? That stiffness of the bond is still present in your expression. So that doesn't go away. And this has consequences. For instance, your heat capacity, again, we stick to the molar one, which is your temperature derivative, then becomes your first squared e to the minus theta vib over t divided by 1 minus e to the minus theta vib over t squared. This might look a little bit messy, but actually this product here has an outstanding place in the history of physics. You can write it also, if you use this u to describe theta over t, you can write it simply as u squared e to the u. So write u equals minus theta vib over t. Then you see here u squared e to the u divided by e to the u minus 1 squared. And this is also known as Einstein function. So only the most cherished expressions, of course, get to be named after somebody. And the way this looks like, if you look at your heat capacity, in terms of gas constants and in terms of characteristic temperatures. So this is basically normalizing things. Then you encounter a curve which looks something like this. And this function gives this behavior, and this was the first time it could be explained, or it matched the experiment for the heat capacity. And this was first shown by Einstein for also what's known as the Einstein crystal. The Einstein crystal is a lattice where the atoms interact harmonically, like springs, right? So if I have a diatomic vibrating harmonically or the perfect lattice vibrating harmonically, it doesn't really matter. You end up with the same expression for the heat capacity. And that's something Einstein demonstrated. And that's also known as Einstein crystals. So for crystals, we call these vibrations phonons. And for molecules, we also call them vibrational normal modes. So this was a great success of this theory that it could, for example, predict or explain the measured heat capacity dependency on the temperature, which previously was not possible. So classical thermodynamics was not able to explain this. Now, I'd like to still come back to the question I asked today, which is, what is the distribution of the vibrational states, right? And so just as for the rotations, we can ask this question: what's the probability for any given vibrational state n? And that will be e to the minus beta h nu n plus 1/2. So just my eigenvalue divided by my q vip. Okay, that's standard. And if you now insert our theta and our vibrational partition function, you will find that this is e to the minus theta over t times e to the minus n theta over t. Right? So my nth state is in this exponentially decaying function. And so, as you would expect, if I plot this Pn as a function of n, I start at 0, 1, 2, 3, and here's my probability between 0 and 1. 0.5. You typically get something up here around 0.8, 0.7. And then for 1, you get something a little bit above 0. And then for the others, because when you sum them up, they have to sum up to 1. But for the others, it's basically 0 already. And particular, if we want to consider the example of N2, again, the theta vib, we've had it before, but again, is 3374 Kelvin at T equals 300 Kelvin. Your probability of your 0th state is 1 to the 1 minus e to the minus 3374 Kelvin over 300 Kelvin times e to the minus 0, which is 1. And so this is e to the minus 11.25, which is the same as 1.31 times 10 to the minus 5, a really small number which you're subtracting from 1 here. So for all intents and purposes, the probability for your 0 state is equals to 1. And then if you calculate it the same way, the probability for the first state, you would find that this matches to a very good degree what we just had subtracted. So if you add the 2, you have exactly 1, right? And that tells you that really all higher excited states are completely negligible for N2 at room temperature. Right. Now, for this example here, actually, this was the bromine case. For bromine, your delta V, your theta vib was 463 Kelvin, and that's the probabilities you would get. Now, before we conclude this discussion, I would still like to make one remark on the weirdness of quantum mechanics, which enters here, right? If you consider now this first excited state, or this one here, right? For N2, it has a low probability. For bromine, it's higher, right? We can imagine this, right? And you know the solutions from Schrödinger's equation, right? And I'm now plotting the probability density of that solution. Okay, and this is your potential. And the parabolic potential, right? And your next state, as you know, should look like this. Now, I'd like you to consider your first vibrational state. What does this mean? This means that if you have your dimer, your diatomic, and let's say this is the equilibrium distance, and let's put it here. That's where your ground state peaks, right? So the most likely distance in the ground state is the equilibrium. That's your bond length, right? You're familiar with. But already just in the first excited state, that's not what you see. What you see, this is for state 1, state 0. For state 1, you either have your atom here or you have your atom here. It's a superposition. So your atom is with equal probability. Is this the equilibrium distance, the first one or the second one, right? You will actually not encounter your second atom at the equilibrium distance. And that probability is 0. So I'd invite and encourage you to develop this awareness of changing state. And all intuition you might have been accustomed to throughout your high school and undergraduate career so far goes out of the window. There's no one equilibrium distance in your first excited state in vibrations, right? Also for electronic states, for instance, equilibrium geometries look different. Right? The repulsion rules we cherish in organic chemistry don't apply anymore, and you might encounter funny angles and geometries which would correspond to minima in the excited state. Right? So one has to be careful, and you have to beware of the quantum state you are in. It matters a great deal. With these concluding words of caution, I'd like to come to the end. Are there any final questions from your side? Doesn't seem to be the case. Then we meet again on Thursday. And I'd like to wrap up on Thursday the vibrational part. We'll be discussing molecules with more than 2 atoms, which seems to be relevant as well.